Hi, folks. A number of you have asked questions about the problems in the course notes relating to the squeeze theorem. So I thought I would make a video going over this with you. So to start, I'm going to talk a little bit about the apartment temperature problem. So in the apartment temperature problem, we had three people, Jerry, Helga, and Felix. And we knew Helga liked the apartment warmer than Felix and Jerry did, and Jerry prefers cooler temperatures than Felix. And so we could write that as a series of inequalities. Helga is greater than equal to Felix is greater than equal to Jerry. And so then in this task, you drew some sample temperature preferences throughout the day for Helga and for Jerry. And at one point, these touch. And at that point, we can essentially conclude that Felix's temperature is the same as Helga and Jerry's, since if Helga and Jerry are equal and Felix is between the two, that Felix would have to be equal as well. And so we can extend this idea to work with limits. And what we'll say with limits is that the although the exact value at a point might be undefined, if we can sandwich it between two other functions that are defined at that point, then we can conclude that the limit of the function at that point is the same as the two other functions. So let's walk through this example here. So we have the function f of x equals x squared sine 1 over x. Now we look at it and it looks like kind of a line with some little fuzzy things in the middle, but let's zoom in quite a bit. So we'll zoom in maybe to about here, and then we'll use the wrench to adjust our y-axis. So let's try 0.01 to minus 0.01. Maybe just a tiny bit more. Let's try 0.001 to 0.01. There we go. So we've got this nice function here where we can kind of see if we trace it that it seems to be approaching zero at the origin, but when we reach the origin, it's undefined. And so the question is, why can we not simply evaluate the function at x equals zero? Or in other words, why is it undefined? And the answer to that is because with this function composition, we first apply the function 1 over x. And when we do that, we see that we end up with an undefined value going into sine. And then if you have 0 times an undefined, the value is undefined. And so what we're looking for is if we can't know the value of the function at x equals 0, how could we know the limit at x equals 0? So the first thing is we're going to just consider by itself the function sine x. And so we see, if we zoom in, that sine x is defined between -1 and 1 inclusive. So what we can conclude from that is that we can conclude that -1 is less than or equal to sine x is less than or equal to 1. And so now working through this, what we can say is if -1 is less than or equal to sine x is less than or equal to 1, then we know that no matter what is being put into sine, it will always be between -1 and 1 as the output. So we can say sine -1 is less than or equal to sine 1 over x is less than or equal to 1. And now we can, to make the part in the middle x squared sine 1 over x, we can multiply each part not quite fitting here on the screen, but I'll zoom in. We can multiply each part by x squared sine 1 over x. And so what we see is that essentially, and remember, we know it's not going to switch the direction of the inequalities because we know that x squared is always positive and the inequalities only switch when you multiply by a negative number. If we didn't have that squared there, we would probably need to consider separate cases, and so it wouldn't work so well. So that's why we're needing a function that's squared when we're working with these inequalities in this particular case. And so now we know x squared sine 1 over x is always going to be between minus x squared and x squared. So now we will come over to here and we'll put in y equals minus x squared and y equals x squared. And what we can see tracing these is that both are defined at 0, 0, or in other words, have limits as x approaches 0 of 0. And so because both of these functions squeezing the function touch at 0, 0, and we know the middle function, the x squared sine 1 over x, is always between x squared and minus x squared, we know that even though we cannot say it's defined at 0, 0 because of the 1 over x, we know that its limit as x approaches 0 is 0. And so that's the basic idea of the squeeze theorem. If you can squeeze a function between two other functions, and the two other functions have the same limits at that point, then we know that the function squeezed between them also has the same limit at that point.